Jake Doyle here from Advanced Test Equipment Rentals.
This is Franz Bosch from BOLAB Systems, the General Manager, and we are manufacturer of high voltage test systems for the automotive industries, especially for the standards ISO 21498 and for Volkswagen 80300.
Today we're going to be going over this new BOLAB test system, high voltage EMC testing, now available for rent. We'll be going over the system and how it works.
The main purpose of this test system is to do inverter testing, is to do DC-DC converter testing, onboard charger testing according to ripple tests, according to load dump tests, and all these kind of testing out of these standards. The main components that are required for doing this kind of testing are, first of all, a 4-quadrant amplifier system, then the artificial network, a high voltage power supply, and then inside of the artificial network there is a built-in capacitor bank, as this kind of testing requires capacitor bank of 10 millifarad, and this is all built in here. So this is the main central stage, this main central unit where we connect the high voltage power supply, where we connect the 4-quadrant amplifiers, and the 4-quadrant amplifier and the high voltage power supply is operating in serial connection. Such a 4-quadrant amplifier system is available starting from 40 amps, 80 amps, 120 amps. We are going up to even 2000 amps. That means if it is an onboard charger that typically captures 30, 40, 50 amps, can be done. DC-DC converters with typically 40 amps, heaters typically 30 amps, or even inverters going up to 800, 1000, 1500 amps can be done with such an amplifier system.
You can pair this system with your own DC power supply or your own chiller. If you don't have those, we have those available for rent as well.
Now we have set up everything. We have connected the high voltage power supply and the 4-quadrant amplifier in series, connected to the capacitor bank for doing the immunity against voltage ripple. That means out of ISO 21498, here we connected our measurement unit, and here we connected filter DUT. And additionally, here is the main control unit and control software, how we do this test, and this is your user interface to act with your DUT. So as the first thing, we have a software, we have a closed loop functionality, and with this closed loop functionality we run a calibration routine. We say start, and now a calibration routine is running. It is generating a voltage ripple, a small voltage ripple from DC to 250 kilohertz. And while this frequency is running, the voltage is measured. The next step, we do the same thing, generating a small voltage ripple, but in the next run we are capturing the current. And out of these values, of these frequency values, we find out, we calculate the impedance. Already done, we went through this frequency range, and now we have a look at the impedance graph. Here in the software we say show impedance graph, and now we have all information of our DUT. You can see here in this impedance graph, we go from 10 Hertz to 250 kilohertz, and now we see there are resonances, and automatically at the red line there is our resonance frequency. That means at 16 kilohertz we have an impedance of 60 milliohm. There is the lowest impedance. That means in that range our current will go up to a very high range. If we want to see where it will go up to, we can activate here in this setup, we can say current RMS, and then we see exactly the red is our current And we see the lower the impedance, the higher the current. And that is why now the standards say in resonance range, the current as it is exploding, it must be limited. And on the other side, the standards say when there is a voltage drop at higher frequencies out of cable inductivities, this must be compensated. And we are using this impedance curve that we find out for these calculations. Now we are doing a small test with this information. I prepared already a small waveform. This waveform, the blue waveform here in this graph, we defined a time of 5 seconds. We defined a voltage of 2 volt at the beginning and 2 volt at the end. And then we say, as an example, we go from a frequency range from 10 Hertz here up to 100 kilohertz. So we try this with a very small voltage ripple. As we have seen in the impedance graph, the current will go up dramatically. So let us now run this test without any closed loop functionality, just as it is. So we load the waveform to the system and then we say start. And as we see here, red is our current. That means here exactly at 16 kilohertz that was determined in the impedance graph. We see here is our resonance. We said there is the lowest impedance, so the current is here at its maximum. And also we found out in our impedance graph that we have another resonance range here in this case at approximately 37 kilohertz. Out of that the current is going to undefined values, the standards say this current must be limited. And this is our next step, what we try out, what we are doing. That means we select here in our closed loop functionality, we select current limitation, and it is said that the ripple current must be limited, not the AC plus DC current, the ripple current must be limited. That is why we select ripple current. And here you see the current was at the maximum of approximately 15 amps. So, for example, we say we want to limit the current at 10 amps. So we set it, okay, and we run the test again. We say load and start again. And now you exactly see that the current is limited at 10 amps. So this is the first process of this closed loop functionality. The next step is, the standard says, here you see the blue, this blue sign interference, this is the reference waveform, the given waveform, and the green is the measured voltage. And now you see the difference that at higher frequencies that there is a voltage drop on the lines, and the standard requires that this voltage drop must be eliminated. This is not allowed. So we do the next step and say voltage regulation. Additionally, now we do the same thing again. We say load the waveform to the instrument and start again. And now you see the voltage stays constant at the required level. And this is exactly what is required in the standard.